Okay, welcome to lesson 2, rates of change in linear and quadratic functions. So in this lesson we're going to look at determining the average rate of change for sequences and functions that are linear, quadratic, and some other types. We're going to determine the change in the average rate of change. And then we're going to use that change in the average rate of change to investigate the concavity over a closed interval. Okay, first up, linear functions. They look like this, don't they? We've seen linear functions. Let me get a little highlighter. We've seen a linear function. So a linear function, the average rate of change over any length input values is going to be constant. We often think of this as a slope. So if we found the rate of change here in this function, we would get the same value as if we found the rate of change here in this interval. It doesn't matter how long the interval is. If we found the average rate of change in this interval, still going to give us the same number. So let's have a go at using that. You'd have to forgive me my writing today. I don't have any writing implement, so I'm using my touch screen and my chubby finger. The table above gives selected values of the function f. Explain why f is not a linear function. So if we look at the average rate of change in these values, so what we want to look at to begin with is the average rate of change in each one. So from 1 to 2, from here to here. So from here to here, we are going to increase the x value by 1, and the change in y is going up by 3. So this is going to give us 3 over 1 with an average rate of change of 3. On this next one, we're going up by 3, but we are going up in the x values by 2. So this one here is going to be 3, oh, my finger's not rubbing, 3 over 2, 1.5. And then looking at the last one there, we are going up by 3 again, but we are going up in the x values by 4. So this one's going to be 3 over 4, which is 0.75. So what we see, therefore, is that is not linear because the rate of change is not constant. Always have to show you're working and give your reasonings. So the f of x is not linear function because the rate of change is not constant. Okay, consider the quadratic function x squared. Complete the table of values for g of x over the consecutive equal length input values below. So we'll do that one first. We're going to have to work that one out. So minus 3 squared, 9. Minus 1 squared, 1, 1 squared, 1, 3 squared, 9, 5 squared, 25. Now, what is the average rate of change on the intervals? So on the first interval, we've got this interval here from minus 3 to minus 1, this one. The average rate of change there is going to be, let me see if I write with my mouse is a bit better. This is going to give us minus 4. On this next one, we're going from 1 to 1, so there's no change there. That one's going to be 0. On this one, we're going from 1 up to 9, so that's going up by 8 over an interval of 2. So 8 divided by 2, that's going to go up by 4. And here we're going to go up by 16 over an interval of 2. So that's going to give us 8. Ooh, nice. What do we notice? What do we notice? Well, this is a quadratic function, and what we notice in this function is the average rate of change of g of x over consecutive intervals of length 2 are increasing at a constant rate of 4. It goes up by 4 every time. So rates of change of g of x are given by a linear function. If we have a constant rate of increase in the rate of change, we can express it as a linear function if we wish. If we have this constant increase in the rate of change over consecutive intervals of equal length, then that will define it being as a quadratic function. We can reverse it. So let's have a look at our essential knowledge. For a linear function, the average rate of change over any length input value interval is constant. For a quadratic function, the average rate of change over consecutive equal length input value intervals can be given by a linear function, meaning you'll have a constant change in the average rate of change over consecutive equal length input value intervals. All right. Selected values for various functions are given in the table below. For each table, determine if the function could be linear, quadratic, or neither. So what we want to do on this one is we want to work out what the average rate of change is in each case. So looking at the interval from here to here, noticing that our x values go up by 1, up by 1, up by 1. Great. Secondly, this goes up by 1, so that's 1. This one goes up by 3. And this one goes up by 5. So this function is going to be quadratic, or I can't write with that. This one's going to be quadratic. The reason it's quadratic is you have a constant rate of change of the average rates of change over consecutive interval values of equal input length size. They form a linear pattern. Okay, let's have a look at the next one. So we are going up from 1 to 2. That goes up by 1, it goes up by 1. So here we've got 1. Here in this interval, this has gone up by 3. This has gone up by 3, so the average rate of change is 1. This goes up by 5. This goes up by 5. So the average rate of change here is 1. So this one is going to be linear, because the average rate of change is always constant. Okay, the last one. We are going up by 2 as we go down, up by 2 here. So 2 over 2, that's going to give us 1. Here we go up by 1. Here we go up by 2. So that means we are going to be having an average rate of change of a half. Here we don't change, so we get 0. So this one has to be quadratic. This one has to be quadratic because the average rate of change of it, the average rates of change decrease at a constant rate of a half. I can't write the thing today. Okay, let's have a little bit of an investigation on concavity. Have a go at working out the average rates of change and then the change in the average rates of change. Okay, so our first interval here, that's going to have it's going to go, notice that the x values goes up by 1 every time, nice and easy. So the y values change by plus 5. So this one is 5. Here on this next interval here, the average rate of change is going down by minus 1. Our next interval, this one, minus 1 to 0. This one is going down by minus 4. This one here, also going down by minus 4. Our next interval, from here to here, from 1 to 2, that's going down by minus 1. And then our last interval, from 2 to 3, The average rate of change there is increasing, and it's increasing by 5. Let's look now at the difference between the average rates of change over these two intervals. So here, the average rate of change has decreased by -6. How about here? What's the average rate of change changing by? It's going down by -3. Between these two, there's no change. Between these two, it's increasing now. It's going up by 3. Between these two, it's increasing by 6. What do we see? Okay. What we've got is this graph from here, around here, like this, is what we call concave down. Here, from this point round up here, this is concave up. Now, when it's concave up is from this interval here. When it's concave down, we've got this bit here. If we were to change these intervals so it wasn't at 0, if it was at -0.1, and here it was at 0.1, we would see that there is a change which would still be positive. Here at 0, something special is happening. So this bit is where it's concave up, this bit is where it's concave down. Now, the change in the average rate of change is negative when a function is concave down. The change in the average rate of change is positive when a function is concave up. This point here is very special. This point here is where there is a change of concavity. When we have a change of concavity, we have what we call a point of inflection, or an inflection point. When we have a change in concavity, we have an inflection point. So our essential knowledge. When the average rate of change over equal length input value intervals is increasing for all small length intervals, the graph of the function is concave up. So when the average rate of change over equal length input value intervals is decreasing for all small length intervals, the graph is concave down. So let me just get my highlighter pen there on the essential bits. It is concave down when the average rate of change is decreasing, and it is concave up when it's increasing, so for positive changes. There's one little bit there, it talks about for small length intervals. For small length intervals, so you have to catch the extreme parts. What does it mean by small length intervals? So for instance, we're only going for small lengths here. Here it's it's positive. Sorry, here the rate of change is negative. Sorry, no, let me get it right. Here the change in the rate of change is negative. Here the change in the rate of change is negative. Here the change in the rate of change is positive. But that's because we're looking at small length intervals. Here's the graph I drew. Imagine if I was to zoom out loads like this. Here, the rate of change is positive. Here, the rate of change is less positive, but still positive. Here it is positive. Here, the rate of change is positive. Here, the rate of change is positive. If we were looking over really long periods, we could get confused and missing a certain part. So this graph actually only changes concavity once, but if a graph was to change concavity twice, let's say we were concave down, then we were concave up, and then we were concave down again, but you chose an interval that skipped right across the period where it changed to concave up, you would miss that particular part of the interval. So that's why it's talking here about over small length intervals. Okay, our last example. Selected values of the functions k, m, and p are given in the table below. For each of the functions, determine if the function could be concave up, concave down, or neither. So what we want to do is we want to find firstly we want to find the rates of change. So here in this first one, we are going down by -3 over a period of 0.1. So we are going down by -3 over a period of 0.1. That's going to give us a rate of change of -30. Here we are going down by 2 over a period of 0.1. So that's going to give us a rate of change of -20. Here we go down by 1 over a period of 0.1. So that's going to give us -10. So the rates of change are increasing. They're getting bigger. Firstly, it's -30. Then it's -20. Then it's -10. We would expect it to move towards 0 and then to positive values. Every time the rate of change is getting bigger and bigger. -30 is the smallest rate of change. -10 is the largest rate of change. So this one is concave up because the rates of change are increasing. Why didn't I think of typing earlier? That was much better. Okay, let's have a look at this next one. So here we're going up by 0.1, going up by 0.1, going up by 0.1. Here we go up by 3. So this is 3 over 0.1. This one's going to give us 30. Here we go up by 3 over 0.1. So again, we're going to get 30. And here we go up by 3 over 0.1. That one's going to give us 30. So this one is neither. It's neither concave up nor concave down, because the rate of change is constant. So if you think about different shaped graphs, all graphs are basically in certain intervals concave up or concave down, unless they're linear. Does it have to be linear? No, it doesn't. If you imagine an absolute value function over certain intervals, it could easily give you this. So an absolute value function is going to go up like that in a straight line, then down in a straight line. If your interval that we're looking at is here, it would be going up all the time, and later it would be going down. But an absolute value function is neither concave up nor concave down, because it doesn't curve. The last one. So yeah, just checking here, we're going up by 0.1 each time. This one goes up by 6, so that one's going to give us 60. This one goes up by 4, that one's going to give us 40. And this one goes up by 2. So that one's going to give us 20. So this function here, or this sequence, we don't know if it's a function. I say it's a sequence because we don't know if there are any x values between 1 and 0.1. But anyway, concave down, because the rates of change are decreasing. All right, then. That's basically the ideas that we're looking at today. Quick recap. For a linear function, the average rate of change is constant over any length input values. For a quadratic function, what we see is the average rate of change over consecutive equal length input values intervals can be given by a linear function. That means it's constant. If they weren't equal length input values, it would be going in the same direction, but it wouldn't be constant. So a quadratic function can either be concave up or concave down. Can't be, it doesn't change concavity because it doesn't have an inflection point ever. Lastly, our essential knowledge about concavity: when the average rate of change over an equal length input value interval is increasing for all small intervals, the graph of the function is concave up. So increasing up, decreasing down. Let's have a go at some exam style questions. The function f has a negative average rate of change on every interval of x on the interval from 0 to 10. The function g has a negative average rate of change on the interval 0 to 5 and a positive average rate of change on the interval 5 to 10. Which of the following statements must be true about the function f, which is defined as the sum of the two functions? Well, the average rate of change of f is negative for all values. G is negative and then positive, but we don't know how negative and how positive. So a negative plus a negative is going to mean we get a negative answer. But a negative plus a positive, that could be positive or negative after we pass 5. So in that particular interval, it would depend on how negative and how negative f is and how positive g is, as to whether the function h is positive or negative. So h is decreasing. No, it's not going to be decreasing. We can't be guaranteed of that. H is decreasing from 0 to 5, definitely. H is increasing from 5 to 10, not certain. H is decreasing from 0 to 5, definitely. H is neither increasing nor decreasing. Well, it will increase or it will decrease, or it could be neither if it perfectly cancel each other out. So D, our last option, seems good. It's decreasing from 0 to 5. H can be increasing, decreasing, or a bit of both in the interval from 5 to 10. Yes, definitely. Our correct answer there is D. Two drones are flying over a given area, and their heights above the ground are changing. The table gives the change in height in feet for the drones over successive 6-second intervals. Which of the following is true about the average rate of change for drone A and drone B on the interval from 0 to 30? All right. So the average rate of changes are equal. The average rate of change of A is greater. So we need to work out what the average rate of change is on the interval given. So that interval is given as 0 to 30. So that's from here to here. So we have to sum all of these up. So 17 minus 4 plus 11 minus 5, that's going to give us 16. So it has an average rate of change of 16. 5 plus 3 is 8. 11, yeah, this one's 16 as well. That means the average rates of change are equal. The function f is given by x squared plus 5x minus 3. For any interval x is less than a, the function has a positive rate of change. Determine the value of a. So if we think about this quadratic function, if we notice here at the beginning, we have a coefficient which is positive, which means we have a concave up function, a smiley face. Our quadratic function is going to look like this, and we are going to have a point of inflection, we're going to have a minimum point here at this value at the line of symmetry. So the symmetry line, if you remember, is given by x sim is equal to minus b over 2a. So we have a formula for the symmetry line of a quadratic function. So that would be equal to minus 5 over 2. We can see that also by factoring. If we complete the square on this one, we've got f of x is equal to, so this would be x minus 5 over 2 all squared minus 5 over 2 squared minus 3. So we could complete the square on that one. This one shows us the value of the x-coordinate of this minimum point, and this bit here, sorry, let me get my highlighter pen. So in fact, in completed square form, if you remember from last year, this one is the x-coordinate of this minimum point, and this expression here, including the sign, is the y-coordinate. So let me just graph that one. We've got 5x minus 3x squared. And we've got y equals x squared minus 5x. Was it minus 5x minus 3? Let me go back. Plus 5x minus 3. So my completed square, that's where I went wrong. It's plus 5, not minus 5. There. So this is x minus 5 over 2. So this is minus 2.5. And we want the positive rate of change, so our answer here is going to be x is greater than minus 5 over 2. Okay, homework for today. I'm going to share a worksheet for you. for you to do. Have a go at those questions. Let me just open it up and show you how it's going to look so you get the right one. We are looking at lesson 2 homework sheet. Here. This is our homework sheet for us to work with today. Okay, thank you very much.